Corrosion. So corrosion of metals, it is an important area of study, and its first importance is economic, that is including the reduction of material losses resulting from the wasting away or sudden failure of pipings, tanks, metal components of machines, ships, hulls, etc. And second is conservation, and this is mainly applied primarily to metal resources. So, what is meant by corrosion? Corrosion is a destructive phenomenon. As we can see from the definition, it is a destructive phenomenon, and it is either a chemical or electrochemical process in which a metal or an alloy is attacked by the surrounding environment, and in extreme cases this corrosion leads to structural failures. So it is also defined as the deterioration of a material by reaction to its environment. So the most common example we know is the corrosion of iron, that is the formation of rust on iron surfaces. So there are different forms of corrosion. So basically corrosion, it can be classified in many ways. First classification is low temperature and high temperature corrosion, and another way is direct oxidation and electrochemical corrosion, and a preferred classification is dry corrosion or wet corrosion. Dry corrosion is also called as chemical corrosion, whereas wet corrosion is called the electrochemical corrosion. So what is meant by chemical corrosion? In this type of corrosion, metal is converted into its oxide when the metal is exposed to a reactive gas or a non-conducting liquid. So this is a chemical corrosion. And now let us see electrochemical corrosion. So in the case of electrochemical corrosion, a hydrous oxide film is formed over the metal surface when it is immersed in a conducting liquid containing dissolved reactive substances. So this type of hydrous oxide film formation causes electrochemical corrosion on the metal surface, and this corrosion takes place at the metal solution interface due to the heterogeneity of the metal surface. So that is, the metal surface is not homogeneous, it is heterogeneous in nature because of the hydrous oxide film formation. So as a result, local anodic and cathodic sites are formed on the metal surface. So these are actually localized areas over the metal surfaces where a certain part of the surface will act as a anodic part, and certain other nearby sites will act as a cathodic part. So this will start the corrosion of the metals. So this is the electrochemical corrosion. Now there are various factors that influence corrosion. As you can see, the nature of the metal, nature of the environment, and the corrosion products, then the temperature, then concentration of electrolyte, electrode potential, aeration, agitation, and also the hydrogen overvoltage and pH of the electrolytes. All these factors influence corrosion. So all these factors can accelerate the rate of corrosion. So there are various theories associated with corrosion. This is how the metal surface corrodes. There are various theories associated with this. So the most common one is the electrochemical theory of corrosion. So let us see this. So corrosion, it is an example of a type of electrochemical reaction since a substance, that is oxidizing agent, oxidizes a metal in its environment. So in the natural environment, oxygen gas is a good oxidizing agent, and most metals have lower reduction potential than oxygen. So therefore they are easily oxidized in the presence of oxygen. So these are the case of metals like iron and all. So all these metals which are easily corroded in atmosphere, they have lower reduction potential than oxygen. Whereas certain metals like gold, silver and platinum, they are called noble metals because they are not easily oxidized, and the reason for the lack of oxidation in these noble metals are varied and sometimes complex. So one of the most familiar corrosion process is the oxidation of iron, that is the phenomenon of rusting. So iron metal is spontaneously oxidized in the presence of oxygen and an aqueous electrolyte solution. So we know that the atmospheric medium, it contains moisture, that is the presence of water molecules, and therefore they all these combination will set up electrochemical cells over the iron surface, and physical strains, that is scratches, dents, bends, etc., present on the iron are more easily oxidized than other areas. So if there are certain physically strained areas on the surface of the iron metal, so those portions are easily oxidized, and this directly relates to physics, that is the way electric fields are generated at the surface of the metal. So stronger fields are generated at a physically strained part of the metal. So that comes from the physics part. So, and as a result of these regions are anodic. That is, in these regions oxidation occurs more easily, and simultaneously different areas, that is the adjacent areas, are cathodic regions where reduction occurs easily. So let us see the oxidation reduction reactions taking place at the surface of an iron metal. So here you can see in the next page, iron atom gives up 2 electrons to form Fe2+. So this is the oxidation step at the anodic sites on the metal surface, whereas the electrons that are released flow through the iron metal to the cathodic regions where they react with oxygen. So at the cathodic sites, what happens is that the electrons released from the anodic sites reaches this cathodic sites, because metal is a very good conductor, and at these cathodic sites oxygen and water molecules combine to form OH minus ions, that is aqueous electrolyte solution. So this is a pictorial representation of this typical reaction, that is the formation of the anodic sites and the formation of the cathodic sites, and what reaction occurs at the anodic site, that is this is the iron metal surface, and from the iron metal surface, if there is a physically strained part or bent like this, iron atom will get oxidized easily here, and Fe2+ ions are formed. So the resultant electrons from this anodic site will reach the cathodic site, and at the cathodic site the atmospheric oxygen and water moisture will combine to form the OH minus ions. So these two reactions are possible like this, and these two half reactions and together it gives an overall reaction like this, that is Fe solid plus half O2 gaseous state plus H2O, giving Fe2+ aqueous plus 2 OH minus aqueous. Now in the next step, once this oxidation and reduction reaction occurs, then the rusting of this iron starts. That is the formation of Fe2O3, which is red colored solid substances formed over the iron surface. And here in this rusting reaction, 4 Fe2 plus ions will combine with oxygen and water to form Fe2O3 and H plus ions. So this is the chemical reaction. Now consider if two different metals are in contact with each other. That is, two different metals will have different oxidation or reduction potentials. Therefore, in such case, the reaction is further more complicated. So, here consider an iron metal in contact with another metal, and in this situation, the electric fields are set up due to the difference in the reduction potential of the two metals, and these fields are stronger than any effect caused by physical strains. Therefore, one metal will act entirely as an anode, while the other metal will act as a cathode. So one can use the standard reduction potential to determine which metal will act as a anode or the cathode. So here, when considering a bimetallic system, that is a system having two types of metals. So the metal with the more positive reduction potential will be reduced, that is, it will act as a cathode, whereas the metal with the more negative reduction potential will be oxidized, therefore it will act as the anode. So here an example is given, that is a copper and a zinc combination. So if copper and zinc are connected electrically and immersed in an electrolyte solution, we have seen this reaction previously, and we might expect that the copper would be the cathode and the zinc the anode based on their relative reduction potentials. So the methods of corrosion protection, this is the next section. So there are different methods to protect metal surfaces from corroding. First is the application of a protective coating. So metallic surfaces, it can be protected from corrosion. The most common method involves application of a protective coating made from paints, plastics or films of noble metals on the surface itself. Example, the coating on tin cans. So these are the this is how we can protect a metal from corroding. That is, a coating of a noble metal can be applied over the metal surface. These coatings form an impervious barrier between the metal and the oxidant. Oxidant will be mostly atmospheric oxygen, but are only effective when the coating completely covers the surface. So if there is any flaws in this coating, then it has been found to produce accelerated corrosion of the metal. This is a drawback. Then there is another method, that is polarize or shift the potential of the metal. So in this method, another method of reducing corrosion is to polarize or shift the potential of the metal, enabling it to act as a cathode rather than the anode in an electrochemical cell. So one example is galvanizing of steel with a coating of zinc. So the iron and zinc then functions as electrodes of a cell. So here the zinc is more readily oxidized metal among these two. Among iron and zinc, the zinc is more readily oxidized, and therefore it functions as an anode and corrodes, while the iron, which functions as a cathode, and it remains intact without corroding. So the Zinc is used up, and a protection is effective as long as zinc remains. So once the zinc is finished off, then the protection is lost and the iron metal will start corroding. And sacrificial anodes, this is another technique. So using sacrificial anodes, this also work on the same principle. That is, the metal which is used for protecting is taken as a anode. That is, it is sacrificed. Therefore, is called sacrificial anode technique. So, and the use of an external electrode is made from a readily oxidized metal. And this form of protection is commonly used on buried pipelines. Then there is a third method for corrosion protection, that is a cathodic protection. Let us see what this is. So cathodic protection using an impressed current derived from an external power supply is a related form of protection in which the metal is forced to be the cathode in an electrochemical cell. So the metal which we need to protect, for example in this case iron, and using an impressed current technique, that is, we give a power supply from an external source, and using this power supply, the metal which is to be protected is forced to act as a cathode. And for example, most cars now use a negative terminal on their batteries as the ground. And besides being a convenient way to carry electricity, this process shifts the electrical potential of the chassis of the car, thereby reducing its tendency to rust. So this is a common technique, this impressed current method. It is used in automobile vehicles to protect the chassis part, that is the base part where the wheels are holded, the base of the vehicle. So it is a metallic part. So in order to protect the chassis from easily corroding, this type of impressed current method, cathodic protection technique, is used. Then another way is by the proper material selection. So we have to select the materials for manufacturing these different parts of automobiles and other parts of the machines wisely. So how is it possible? So use corrosion resistant materials including plastics and non-metallics in severe environments. This is one method. Then avoid dissimilar metal couples, that is bimetallic systems. We saw this bimetallic system here. So like dissimilar metal couples should be avoided because there is a difference in the electrochemical reduction potential, and one metal will act as a cathode and the other will act as an anode, and the corrosion starts easily. So such methods should be avoided. Then avoid the use of back-to-back structural shapes such as box beam sections and unit truss. So all these type of structural shapes of different parts, metallic parts, should be avoided. Instead, we have to consider shapes like C shape or a D shape, in which the bends are all minimum. So the corrosion of such these parts, corrosion in these bends will be reduced. So this is another method. Then you can avoid the use of alloys susceptible to stress corrosion. So these are the four ways, four things which we should be careful while selecting the material. Then corrosion inhibitors can be used. So corrosion inhibitors are chemical substances which are added to solutions in contact with metal. So these inhibitors are required in an antifreeze solution in automobile cooling systems. This is an example for where we use corrosion inhibitors in automobile systems. So what these corrosion inhibitors are doing? They will prevent either the anode or the cathode reaction of corrosion cells. So let us see the common anodic inhibitors, anodic corrosion inhibitors, which are sodium phosphate and sodium carbonate. And cathodic inhibitors are zinc sulfate and calcium or magnesium salts. All these will act as inhibitors, corrosion inhibitors. And one way they can do this is by forming insoluble films over the anode and cathode sides of the cells. So this is how the corrosion inhibitors acts. So certain paints, new forms of paints which are recently developed, take the advantage of this property, and they are also helpful in eliminating corrosions on the metal surfaces. Then there are corrosion monitoring techniques. Different corrosion monitoring techniques are there, and using these techniques also we are able to identify the rate of corrosion. We are able to get a proper feedback of corrosion. That is, these are quantitative methods which measures the rate of corrosion, and it also helps in controlling and preventing the corrosion process. So let us see what are the different corrosion monitoring techniques. So first is corrosion coupons, that is weight loss. This technique will act on principle of weight loss. So the weight loss technique, it is the best known and simplest of all corrosion monitoring technique. So how this method is working? This method involves exposing a specimen of material which is called the coupon. Okay, this specimen is exposed to the process environment for a given duration. So for a given duration we are exposing this specimen of a material to this corrosive environment, and then removing the specimen for analysis. So after a given duration we are taking this specimen and we are analyzing this specimen, like how much weight is lost from the sample. So the basic measurement which is determined from corrosion coupons is weight loss. The weight loss taking place over a period of exposure being expressed as corrosion rate. So the simplicity of the measurement offered by the corrosion coupons is such that the coupon techniques forms a baseline method of measurement in many corrosion monitoring programs. So these are the advantages of weight loss coupons. That is, this technique is applicable to all environments, gases, liquids and solids or particulate flow. And then visual inspection can be undertaken. We can remove the specimen from this environment and visually we can inspect this specimen. Then the corrosion deposits can be observed and analyzed. Then the weight loss can be readily determined, and corrosion rate can be easily calculated. Then localized corrosion can be identified and measured. Then inhibitor performance can be easily assessed. So these are the advantages of this technique. There are also certain disadvantages of this technique. That is, if a corrosion upset occurs during the period of exposure. So in such a case, the coupon alone will not be able to identify the time of occurrence of the upset, and depending upon the peak value of the upset and its duration, may not even register a statistically significant increased weight loss. So here we are not able to correctly measure or analyze this rate of corrosion if the process of corrosion is hindered in some way or the other. That is, if an upset is occurring during this process, we are not able to statistically register this change in the weight of the specimen. So therefore the coupon monitoring is used in combination with other techniques like ER or LPR measurements. So let us see this ER monitoring technique, that is electrical resistance monitoring technique. So in these ER probes can be thought as an electronic corrosion coupons. So here, like this coupons, the ER probes provide a basic measurement of metal loss, but unlike coupons, the value of metal loss can be measured at any time. So this is the main basic difference in these two techniques, and it is frequently as required, while the probe is in situ and permanently exposed to the process stream. So this is actually a probe, and which is permanently exposed to this environment, that is process stream. Process stream means if the environment in which the metal is exposed. So here the ER technique measures the change in ohmic resistance of a corroding metal element exposed to the process stream. So what is this technique measuring? It is actually measuring the change in ohmic resistance of the corroding metal element which is exposed to this corroding environment. So the action of corrosion on the surface of the element produces a decrease in its cross-sectional area with a corresponding increase in its electrical resistance. So this is the basic principle behind this ER monitoring technique. So the increase in resistance can be related directly to this metal loss, and the metal loss is actually a function of time, that is the corrosion rate. So this is how we are monitoring the rate of corrosion using the ER monitoring technique. So these also have several advantages over the corrosion coupon technique. The probe, it remains installed in line until operational life has been exhausted. So this probe is permanently installed in that particular part of the metal. So until that operation life of this probe has exhausted, this probe is installed there, and they respond quickly to corrosion upsets, and it can be used to trigger an alarm. So if there is an onset of an electrochemical reaction in some part of this specimen, suddenly this probe will catch up this upsets, the corrosion upsets, and it will quickly trigger an alarm. So the response time of ER monitoring is far shorter than that of weight loss coupon. So response time is very short. It means it is very quick in action. So here the ER probes are available in a variety of elemental geometries, metallurgies and sensitivities, and it can be configured for flush mounting, such as pigging operations can take place without the necessity to remove probes, and a range of sensitivities allows the operator to select the most dynamic response consistent with process requirements. So these are the advantages of using ER probes. So there are a range of sensitivities available for these probes, and a person can select suitable probes which requires this particular process in which he is monitoring. So these are the common advantages of ER monitoring. And let us see this linear polarization resistance, that is LPR monitoring technique. So this is based on a complex electrochemical theory. So here, for purpose of industrial measurement application, it is simplified to a very basic concept, and in fundamental terms, a small voltage or a polarization potential is applied to an electrode in solution. So here at first what is done is that a small voltage is applied to an electrode in solution. Then the current needed to maintain a specific voltage shift is directly related to the corrosion of the metal, corrosion of the surface of the electrode in the solution, and therefore by measuring the current, the corrosion rate can be derived. Here if we need to maintain a specific voltage shift, typically for example here a 10 millivolt is given here in the bracket. So if you want to maintain this specific voltage shift, then this is actually directly related to the corrosion process, and by measuring this current, by measuring the current produced, the rate of corrosion can be derived from this technique. So these are the advantages of LPR technique given in your textbook. First is that the measurement of corrosion rate is made instantaneously. So it is instantaneously possible to measure the corrosion rate, and it is a more powerful tool than either of the two techniques which we initially mentioned, that is the Coupon and the ER technique, electrical resistance technique, where the fundamental measurement is metal loss and where some period of exposure is required to determine a corrosion rate. So in this Coupon technique and ER technique, here some period is actually required to expose the metal to this determinable environment. So unlike this technique, this LPR technique is even more powerful, and it does not require the corrosion or a major weight loss of the metal is not necessary in this type of technique to be monitored. And the disadvantage of this LPR technique are that it can only be successfully performed in relatively clean aqueous electrolytic environments, and it will not work in gases or oil water emulsions, or where fouling of the electrodes will prevent measurements being made. So fouling means the loss of sensitivity of that electrode surface. In such cases, this technique will not work. So extreme sensitivity is required for this LPR technique. It is it can be performed only in clean aqueous electrolytic environments. Then we have many other methods like this. There is also galvanic or potential monitoring technique measured in your textbook. You have to learn that also. In galvanic monitoring technique, it is also called as zero resistance ammetry, ZRA, and it is another electrochemical measuring technique. Here also we are using a probe, that is ZRA probe. Here two electrodes of dissimilar metals are exposed to the process fluid. We are using two electrodes in this probe, and these two electrodes are made of dissimilar metals, and it is immersed in the process fluid, and when immersed in solution, a natural voltage, that is a potential difference, exists between the electrodes, and the current generated due to this potential difference relates to the rate of corrosion, and which is occurring on a more active of the electrode couple. So here if in this probe, if there is a corrosion occurring, then a current will be generated between these probes, and from this current the rate of corrosion can be measured. So the galvanic or potential monitoring is applicable to the following electrode couples, which are the bimetallic corrosion, then cervic or pitting attacks, then corrosion assisted cracking, corrosion by highly oxidizing species, weld decay, etc. Then galvanic current measurement has found its widest application in water injection systems, where dissolved oxygen concentration are a primary concern. So in such cases, oxygen leaking into such systems greatly increases galvanic currents, and thus the corrosion rate of steel process components. So in such environments also, galvanic current measurements are found to be widely applicable, and galvanic monitoring systems are used to provide an indication that Oxygen may be invading injection waters through leaking gaskets or deaerated systems. There are also other techniques like specialized monitoring, biological monitoring. Biological monitoring is actually mostly done to identify the presence of a sulfate reducing bacteria called SRB. So this is an anaerobic bacteria which consumes sulfate from the process stream and generates sulfuric acid. So sulfuric acid will easily attack the metal plant parts. Plant means here the plant is referring to the industrial parts. So, and there is also sand or erosion monitoring. So in these devices, these are designed to measure erosion in a flowing system, and they find wide application in oil, gas production systems where particulate matter is present. Then you also have this hydrogen penetration monitoring, and in acidic process environments, hydrogen is a byproduct of corrosion reaction. So here in such cases, hydrogen generated in such reactions can be absorbed by steel, particularly when traces of sulfide or cyanide are present, and this may lead to hydrogen induced failure by one or more of several mechanisms. So the concept of hydrogen probe is to detect the amount of hydrogen permeating through the steel by mechanical or electrochemical measurements, and to use this as a qualitative indication of corrosion rate. So this is how these are the different corrosion monitoring techniques, and this is the last section of this unit. Thank you.